Uh, excuse me. So what I'd like to do today is basically go back and talk about Karp-Luby and tell you about a fairly non-trivial improvement on Karp-Luby and how it uses geometric random variables. So it's a very sort of neat application of geometric random variables. So let's just sort of revisit what Karp-Luby was doing, and so I'm just going to show you my notes. So remember that our aim was to get an FP-RAS for counting the number of satisfying assignments in a DNF, disjunctive normal form. And what Karp-Luby gave is an algorithm essentially that's a 1 plus minus, it's a 1 plus epsilon approximation. It means that it outputs a 1 plus minus epsilon approximation to the true value, the number of satisfying assignments to a DNF, with probability 2/3, and we can always boost this probability. And the key was that Karp-Luby runs in m square n divided by epsilon square. Remember, m is the number of clauses, n is the number of variables. So it's quadratic in the number of clauses, and you might want to think of a situation where the number of clauses is really large and the number of variables is somewhat smaller. And so what Karp-Luby did is, the algorithm is a very clever trick. So what it says is, well, let's look at the set of satisfying assignments to the ith clause. Okay, so you have a set of satisfying assignments to the ith clause, and because it's a DNF, you want to estimate the union of the size of the union of these sets, which we denoted as A. Now we can determine the size of each individual set S sub I, so it's easy to determine the sum. So now we sort of abstract this problem out. We say we have a collection of sets. We know the size of each set, so we can estimate the sum. And we want to estimate the size of the union. We want an algorithm that would estimate A divided by B, which is the fraction. So once we estimate this fraction accurately, we can multiply with B and get an estimate for A. And so the trick here is to use what's called some kind of importance sampling. So the algorithm, okay, so let me actually sort of talk about the idea. The idea is we construct a set of tuples x comma I, where x is an assignment and x satisfies the ith clause. So the number of tuples is exactly B, right? Because for every I, there are S sub I choices of x. So there are that many tuples that satisfy there are that many tuples. So moreover, we can sample uniformly at random from this set, right? The key is that we can sample tuples uniformly at random. So once we get a uniform random tuple, then we do what's called an association rule, right? So we said that we associate x to a unique clause. So we associate x to the clause, we associate x to the clause, to the satisfied clause of minimum index. So every x is going to be associated with only one clause that it satisfies, which means that x does not satisfy any other clauses, right? If x is associated to the ith clause, it does not satisfy the I primed clause for all I prime less than I. How many tuples correspond to associations? Exactly A, right? And so now we can pick a uniform random tuple, check if it's an association, and that's the algorithm that gives you Karp-Luby. So Karp-Luby chooses some number of samples, and that's T. Now for each sample, the way it's let me refer to these as trials, right? So this is a trial. So in each trial, what happens? We pick a clause uniform with probability proportional to the number of satisfying assignments. Then we pick a uniform random satisfying assignment to the ith clause. So what we get is a tuple, x comma I. We got I from here, and we got x from here, and x comma I is a tuple. This is a uniform random tuple, and now we simply check, is this tuple an association? If it is, we set it to 1, otherwise you set it to 0, and then we compute the fraction and we do the usual sort of Chernoff arguments. Now, the weakness of this argument, or rather the inefficiency of this argument, was we discovered that the number of samples required, the number of trials required, is essentially you need theta of m trials. You need omega of m trials for any conversions. For each trial, determining whether it actually is an association requires an extra m. And this gives you an m times m, which is m squared. Right? So far so good. Now, and this gives you m square n because you need m times n to do this. And the question was whether one can improve the dependence on m from quadratic, and remarkably one can actually improve it to linear. Okay, so let me now revisit that idea. So I sort of told you very quickly towards the end, and I'd like to walk through it again. So now let's do things differently. Now let's do things differently, and maybe I'll write this down. I'll write this down again, and I'll call it the improved Karp-Luby, which is, I guess, really the improvement was Karp-Luby-Madras was the improved algorithm. So if I understand correctly, Karp-Luby was the conference version, which had the first algorithm, and then Madras came and improved it. So remember, we wish to estimate the union of SI, I going from 1 to m, divided by the sum of SI, I going from 1 to m. I call this A divided by B, and I'm going to refer to this as mu for convenience. Okay, so now let me sort of describe this at a high level, and then I'll give you a more concrete. I'll write out the individual steps. Pick a uniform random tuple x comma I. Okay, now let the count of x be actually the other way around, the number of I such that x sub I is a tuple. What does that mean? Count of x is the number of clauses that x satisfies. Right? So let's look at the following random variable. Pick a uniform random tuple and output 1 divided by c of x. Okay? So what is the expectation? Now, remember, we're choosing tuples of 1 divided by c of x. So this expectation, so we picked tuples uniformly at random. So that's the sum over all tuples, right? And I did 1 divided by b because that was the probability of picking a uniform random tuple, picking a tuple x sub I, 1 divided by c of x. Now note that x appears exactly c of I times in this sum, and therefore this will give you a divided by b exactly. So does this make sense? So this algorithm, which is instead of doing an association, one could pick a uniform random tuple, one could go ahead and compute c of x just by walking through all the clauses and output c of x, and one could then repeat this O of m over epsilon squared times. And as an exercise, just show that this works. The analysis is identical to the other Karp-Luby. Analysis is nearly identical. I should say nearly identical to the original Karp-Luby algorithm. Okay, does this make sense? So there is no association. I'm going to pick a uniform random tuple and then I output 1 divided by C of x. Okay, so is this clear? Okay. Now the improvement is I'm going to pick a uniform random tuple. So this is again going to recall that this is going to be m squared, right? Because this is m times you're doing this box here, and then to compute c of x requires m time. So that's going to be m squared. But now let me give you an improvement. So the idea is I'm going to pick a uniform random tuple. I'm going to output a random variable whose expectation is 1 over c of x. Okay, so how is that going to work? So how does this work? So repeat the following. Okay. So what you do is you pick a uniform at random clause. Let's say the ith clause. Check if x satisfies the ith clause. Okay. Now let's call this a success. And what you do is you repeat until success. Then you output the number of repeats. Okay. Does this make sense? So you fix an I. You picked a uniform random tuple. You're going to pick a uniform at random clause. So maybe this is bad notation on my part. So this I has nothing to do with this I. So maybe I will just I'll refer to this as J. Right? So you repeat until you pick a uniform random clause and then you check if x satisfies that clause. If it does, you succeed and you're done. You keep repeating this uniform at random until you succeed. Okay, does this make sense? Okay. Now question. For a single trial, so this is my trial here, what is the probability of success? For a single trial, what is the probability of success? Remember, you're fixing x.
1 over c of x.
No. C of x over m. Right? Because you picked a uniform random clause and you're checking if it satisfies. So it's c of x divided by m. So what's going on here? So think of it as you have a coin whose heads probability is cx over m, and you keep flipping this coin until you get a success. And then what you're outputting is how many flips were performed. And this is called a geometric random variable. So let's take a detour now. Let's talk about geometric random variables and their properties, and then we will come back to an analysis of Karp-Luby. I will not be able to give you a full-fledged analysis, but I will sketch out sort of the main parts. It can be fairly technical to do the improvement, but you'll see that there's something, you should be able to see most of the ideas. All right. Okay. So, geometric random variables. So given a coin, keep flipping independent trials until you see a heads, the number of flips. This is the random variable, right? It's the number of flips. Okay, so what is the probability that x takes a value k? Well, you had to have tails for the first k minus 1 flips times p, where p is the heads probability of the trial, of the coin. Okay? Now, one of the key properties of geometric random variables is called the memorylessness. The memoryless property. Okay, so what does the memoryless property say? It says, let's condition on x being greater than k. What is the probability that x is equal to t plus k conditioned on it being more than k? So any thoughts, any guesses here? What is the probability? Can you express this in terms of the probabilities of t and k, so on and so forth, instead of looking at the expression? So what this says is you did a bunch of coin flips. You have not seen a heads up to k trials. What is the probability that you are going to see a heads within the next t trials? Right? Because this is the probability that x, or not within, but exactly at t plus k and tails before. Does this make sense? I'm sorry? Is the probability that x is equal to t. Right? Because the failures, the first k failures do not affect subsequent trials. And this is called the memoryless property, which is sort of one of the key uses of geometric random variables. As an exercise, you can prove it. It's fairly easy. You can actually just use these expressions and use standard. You just sort of do the algebra, and it should work. Okay, but the expectation happens to be exactly 1 over p. Okay, and this can be proven again. So let me just prove it over here, because it's a nice exercise of using the memorylessness. So what is the expectation of x? Well, I can say it's the probability that x is equal to 1 times the value here, plus the probability that x is greater than 1 times the expectation of x conditioned on x being greater than 1. Right? So this is equal to p. That's the probability. Plus this is 1 minus p. Okay. Now what is this by the memorylessness? So my first trial was tails. It's not e of x. It's almost. It's e of x plus 1, right? Because the first trial was a failure. Right? It's the expectation of x plus 1. And you have a plus 1 because the first trial was a failure. I mean, if you actually just put e of x over here, the e of x will, you will get an incorrect bound. So let's crank this out. So that's p plus the expectation of x minus p times the expectation of x plus 1 minus p. Okay, and so this is going to cancel out with that. This is going to cancel out with that. And so what you just get is that the expectation of x is 1 over p. You can also prove that the variance of x is 1 over p squared. Again, exercise. You can actually crank out the formula exactly, or you can use memorylessness. Use the memoryless property, or just do the algebra. Okay. So this is a geometric random variable. Sorry. Let me just fix that. And another random variable of interest is, so the negative binomial is essentially it's a generalization, or it's a sum. It's keep flipping until you get r heads, and this is the negative binomial where you have the parameter is you have r as the number of heads and p. And this you can think of as really is the sum of xi, I going from 1 to r, and xi's are independent, geometric random variables with this parameter p. Right? So you keep flipping until you get r trials. Now, one thing that we can immediately talk about, what about tail bounds for the negative binomial? So let's just say you have a coin. There is a coin, has unknown heads probability. Right? Keep flipping until you see r heads, and suppose there were s flips. Output r over s as the estimate for p. So how good is the estimate? What should r be to get a good estimate for p? Any thoughts? Try to, let's just think about it intuitively. How many heads do you need to see to get a good approximation? Okay, so maybe let's turn this around. Suppose we want a 1 plus epsilon approximation for p. How many flips do I need? How many flips? So let's ignore, how many flips do I need? Let's ignore the delta, the confidence parameter. How many flips do I need to get a 1 plus minus epsilon approximation for p? Assume I told you what p is. Yes, any thoughts? How many flips? Chernoff bound, anyone? As a function of p and epsilon, tell me how many flips you need. Okay? So, let's continue. If we want a 1 plus epsilon approximation for p, then the number of flips you need is 1 divided by p epsilon squared. But if you did that many flips, then how many heads do you get? If you did these many flips, how many heads are you going to see? So what is the expression? 1 over epsilon squared. Exactly. So the number of heads you need is independent of p. So when you look at it this way, when you look in terms of the number of flips, there's a problem because you have to express the number of flips in terms of p, which is exactly what you're trying to find. But if you express it in terms of how many heads, then it is only dependent on the epsilon, it's independent of p. So, which is why, sometimes looking at the negative binomial is convenient, because you can say keep flipping until you see. So if r is, and I put equality, but I basically mean like, maybe I should put thetas over there, is 1 over epsilon square, we get a 1 plus epsilon approximation for p. Okay, does this make sense? This is a really important point. When you talk about the negative binomial, you want a 1 plus epsilon approximation for p, then you can simply specify how many heads you need to see. You do not have to specify it in terms of p. There's no dependence on p. So think of it as analogous to an additive bound. When you want an additive bound of epsilon, it only depends on epsilon. There's no dependence on p. When you want a multiplicative bound, well, then the dependence on the number of flips depends on p. The number of flips depends on p, but the number of heads is independent of p. Okay, so let me write this down again. I'll write this as a theorem. I'll say let r be, let's say omega of log 1 over delta divided by epsilon squared. So maybe what I mean is let r be greater than, there's some constant that I'm going to put there that I haven't yet figured out. Let r be greater than that. Then the probability that r divided by s is not in 1 plus minus epsilon of p. This is at most delta. So this says keep flipping until you see, we will figure out the constants. We will put this constant down later. But keep flipping until you see, essentially the way to think of this is until you see at least 1 over epsilon square heads. The estimate is a 1 plus minus epsilon approximation. Okay? I'm not going to do the entire proof over here, because I'll just say that what is the probability that your estimate was more than 1 plus epsilon times p. Yes. Sorry? I did. I started the recording again. Yes. Okay. So we saw r heads, which means that r divided by s is greater than 1 plus epsilon times p. Now what does that mean? It means that s is less than equal to r 1 plus epsilon times p, and just using some standard approximations, okay, we get that. Now the specific constant that I have worked out over here, I set r is equal to 13 log 2 over delta divided by epsilon square. So let's sort of rework this. We did 1 minus epsilon over 2 r divided by p flips and saw at least r heads. So I believe someone had asked the question of, but the negative binomial, you can't apply the Chernoff bound over there because each of those random variables are actually unbounded, which is absolutely true. But it turns out that by just flipping your viewpoint, you can apply the Chernoff bound for just the binomial tail to understand things about the negative binomial. So what am I saying? We saw r heads, but we actually did few flips. We did less than 1 minus epsilon over 2 r divided by p flips, meaning if your estimate was too large, it means that you got r heads with too few flips, which means we did suppose in this trial you did exactly these many flips, you are going to see more than r heads. And now you can apply the Chernoff bound because the number of flips is fixed, and you're looking at how many heads you got. Okay? Because we know that the expected number of heads is this. The expected number of heads is 1 minus epsilon over 2 times r, but what we saw was more than r heads. So now we can apply the Chernoff bound. We can say that the probability that the number of heads was more than 1 plus epsilon over 2 times the expected number of heads is at most, now let's crank the numbers, expectation of the number of heads, right? And the expected number of heads was this, so this is less than equal to times 12 times 1 minus epsilon over 2. R is like 13 log 2 over delta divided by epsilon square. So you work all of this stuff out, and what you get is that this is going to be less than delta over 2. So this is the probability. The probability of overestimating is less than delta over 2. Now you exercise, prove the probability of underestimating is also less than delta over 2, and this will complete the proof. So this is, you're saying that you're getting tail bounds on the negative binomial by looking at tail bounds of the binomial, which is, this is the Chernoff bound here. It's actually funny that if you search, if you Google, which I did, for tail bounds of negative binomials, you actually get very little. What I got was actually a PDF by someone, by a researcher who said, this was written maybe about 4 or 5 years ago, fairly recent, saying that the pain, it was something about the pain of finding tail bounds for the negative binomial, and he said that if you try to apply direct tail bounds on the negative binomial by writing it as a sum of independent geometric random variables, you go through a lot of pain because these are unbounded. You cannot apply standard methods, and you try to apply moment generating functions and all, and it becomes really messy and complicated. And instead, there's a very simple proof, which I mean, he also observes that after doing a lot of work, he arrived at this, that essentially, if you look at it in terms of a Chernoff bound, in terms of a binomial distribution, then you can get concentration. So what this says, again, is to go back, you keep flipping until you see 1 over epsilon square heads. The estimate that you get is a 1 plus minus epsilon approximation to P. Okay, I'm going to pause here, and I will take questions. And then after that, I will continue with the remainder. Go back to the recording because I'm going to sort of explain this proof again and say that if R over S is not in 1 plus minus epsilon of P, meaning that we did not get an accurate estimate, we either overestimated or we underestimated. Let me first compute the probability of overestimating. That's the probability of overestimating. So we saw R heads. If we overestimated, this means that we did very few flips. So let's go back and compute how many flips we did. So if R over S was more than 1 plus epsilon times P, then S must have been pretty small. So S is R divided by 1 plus epsilon rho. I just use a simple, like a basic Taylor approximation, and I get this is 1 minus epsilon over 2 R over P. Does this make sense? Any questions about this? Right, this is just saying that 1 divided by 1 plus epsilon is at most 1 minus epsilon over 2, and this holds for all epsilon in 0, 1. Right? So I just flip that 1 minus epsilon to the numerator. Okay. So what this means is we did 1 minus epsilon over 2 R divided by P flips and saw R heads. What we expect is really to do R divided by P flips. We expect to do that many flips to see R heads, but we actually did fewer flips. So if you did these many flips, you actually should be seeing these many heads. Now this is where we switch our view from fixing the number of heads and seeing how many flips to fixing the number of flips and seeing how many heads. This is really important. This is where, apologies for overloading the term flip, but this is where we flip our view. So we flip our view from the negative binomial fixes heads and looks at flips. The binomial, which we know how to deal with, fixes flips and looks at the number of heads. So in this case, we're going to fix the number of flips now and see how many heads we got. So in this situation, when we overestimated, we did 1 minus epsilon over 2 R divided by P flips and actually saw more than R heads. So the expected number of heads that we saw, that we should see, the expected number is just 1 minus epsilon over 2 times R, but what we saw was R heads. So that means that the observation deviated by more than 1 plus epsilon over 2 times the expectation. So I haven't done all the algebra here. But if this is the expected number of heads, and that's how many heads you actually saw, that means that you saw this event where the number of heads was more than 1 plus epsilon over 2, because the product of this is it's 1 minus epsilon squared. So this is the event that the number of heads you saw was much more than the expectation. That's what happens when you see R heads. And so now you crank through the Chernoff and you get your probability bound. And so that gives you the probability of overestimating. And you basically use a similar tail bound, use the lower tail bound, and you can also get the probability of underestimating. Any questions? So, yeah. Go on.
So my question is, expectation number of heads is 1 minus epsilon over 2, but then we use Chernoff bond by calculate probability of number of heads greater than 1 plus epsilon over 2.
times this. So, okay, so what is this? This is 1 plus epsilon over 2 times 1 minus epsilon over 2 times r, which is 1 minus epsilon square over 4 times r. So r is greater than this. My point is, if the expected number of heads is 1 minus epsilon over 2 times r, and you saw r heads, then essentially, okay, so what am I? I'm just saying that r heads is more than 1 plus epsilon plus 2 times this expression. Does that make sense?
Yes.
So the number of heads I saw was 1 plus epsilon over 2 times this expression. Like r is greater than 1 plus epsilon over 2 times this. So therefore r is a deviation of more than 1 plus epsilon over 2 over the expected number of heads. There was another question?
Yeah, I had a question.
Mhm.
It was more like, could you like clarify on the logic that you used to go from like figuring out our estimation error almost to
So
fixing the number of flips?
sure. So
How do you convert that?
so think of it as maybe this is worth writing down. Um, so remember, we saw r heads. We did s less than 1 minus epsilon over 2 r divided by p flips. Right? This is where we got. Like, I haven't done any change yet. This means that in so imagine the following experiment. You saw r heads. You did s flips. But keep flipping until you did these many flips. So at that point, keep continuing until you did more flips, until you did 1 minus epsilon over 2 r divided by p flips. So that means, so sort of in this world, in the world where you saw r heads with fewer than 1 minus epsilon over 2 r divided by p flips, in that world, if you kept flipping until you saw these many, until you did these many flips, we will see at least r heads. And then the logic follows. Does this make sense? So what you do is you do a thought experiment. You say, well, I saw r heads. I only did a few flips. So let me keep flipping until I did these many flips. And then at that point, I can fix the number of flips, and I said I must have seen more than r heads. Any questions?
I have a detailed
Yes.
question. When you prove the underestimate part,
Mm-hmm.
I guess you still need to use some Taylor expansion on 1 over 1 minus epsilon.
Exactly.
Is it going to be approximated by?
That's your job as the scribe.
Yeah.
That's what you need to figure out. That's the exercise. Figure out what is the right expression to put over there. Yeah, you're right. You'll need to do a Taylor approximation over there. But it'll be easier.
Thanks.
Could you repeat that?
So I guess what Yatong was saying was basically that, to go from here to here, I had to move this 1 plus epsilon to the numerator, and I did some kind of Taylor approximation. So in the other case, in the underestimating case, you'll have s is greater than r divided by 1 minus epsilon times p. So you have to move the 1 minus epsilon to the numerator, and you have to have some approximation of that form which goes in the opposite direction. But I mean, it's the same approximation. You just flip things, you move things around. Okay? Okay, so that is the discussion of the negative binomial and the geometric random variable. So let's kind of step back here now. Let's sort of step back and let's now do an improved Karp-Luby based on this. Okay. Now what I'm going to give you is not the most optimal description, but it will improve the dependence on M. So recall, let's go back to Karp-Luby. What we did, remember, we want to pick a uniform random tuple and we want to output 1 divided by C of x. I can construct a random variable I can construct a geometric random variable. Now remember, for a single trial, the probability of success was Cx by m. So what is the expected number of trials for a success? This is a geometric random variable. That's the parameter. And what is the expectation of a geometric random variable? What is the expectation of a geometric random variable with this being p? It's the reciprocal. So it's that. And this, m divided by c of x, well, that's exactly what I'm looking for over there. So now let me write out the improved Karp-Luby. Repeat t trials. So I'm not going to tell you what t is right now. Repeat t trials. So let me actually do this a little bit more formally. I'm going to set x is equal to 0 and t is equal to 0. Okay. I'm going to put some condition here which we'll get to. Let me pick a uniform at random tuple xi. Okay. X. So remember that the I is going to become irrelevant. Pick a uniform random tuple. Okay, so I want to output 1 divided by Cx. Right? Because that would give me my desired random variable. If I pick a uniform random variable xi and I output 1 divided by c of x, the expected value of that is exactly a divided by b. So I need to output this. Instead, what I can do is I can construct a geometric random variable whose expectation is exactly that. Right? I can get a geometric random variable so what I could do is, so now what I have is I can let me think about how to say this, or I'll say generate y, which is a geometric random variable distributed according to Cx divided by m. Okay, and let's do this again. This is not the most efficient way of doing this, but what I can do is estimate the expectation of y up to 1 plus minus epsilon, right? This is the same as before, like same as the negative binomial discussion. You keep flipping until you get 1 over epsilon square successes. Then let me just write something here. I'm going to increment the total sum, increment the total number of trials, and then I'm going to output x divided by t as the estimate. Okay, so I haven't told you how many times I need to do this, but we'll get to that. So remember, what am I trying to do? I said that the expectation of 1 divided by c of x, this is exactly equal to what I want. So I can construct this geometric random variable. How do I get the geometric random variable? I pick a uniform random clause and I check if x satisfies that clause. And I keep repeating until I get a success. So for a single trial, the probability of success is cx divided by m. The geometric random variable has an expectation which is the inverse of that. So I have a geometric random variable. The expectation of this geometric random variable is precisely m divided by c of x. I can apply the discussion earlier to get a 1 plus minus epsilon approximation to the bias, which is basically a 1 plus minus epsilon approximation of this. You can think of it either way. Okay? So I get the expectation. So this is like the expected number of flips that I need to see, which is just the inverse of the probability. So I can either estimate this or estimate the bias. We can do it different ways. It doesn't matter. But then I'm going to basically say, okay, so this is my estimate. This is my estimate for 1 divided by c of x, and I'm just going to add it to a rolling sum. And then I finally divide by the total number of trials that I did. Okay? How many times do I need to do this? Okay, this is a bit tricky now. This is a bit tricky now. How many times do I need to do this? So I'm going to work out some of the logic here. I don't know if I have time to do a full proof. I might eventually just put up some notes with the full proof or leave some exercises so that you can fill in the blanks. Okay? So I'll just say while x is less than c over epsilon square, c is going to be some constant. So there's our friend, the 1 over epsilon square popping up here. So if you think about this whole box over here. No, not t. X. This is the point. Good observation. It's not t. That's right. That's right. No, that's a good point. I think you're seeing like there's something different. I could have put t to be c over epsilon square, but that's actually not going to work because this quantity is less than 1. So I may have to do more trials than c over epsilon square.
Okay. But then won't the number of trials that you do depend on? I guess it should depend on A over B.
Exactly. The number of trials is going to depend on A over B, but that's what should happen. That's exactly right. So let's go over this now. Let's go over this. Let's try to see. I mean, let's do both. I mean, let's try to get a concentration. We'll do the concentration in a bit. But what I first want to do is to basically give you a sense of the running time. Do you kind of understand what's going on? This has an expectation of 1 over c of x. So this is some box that's just going to spit Let's just say it's going to spit 1 over c of x up to 1 plus minus epsilon. Let's ignore that 1 plus minus epsilon. Let's just assume that it's going to be accurate. Let's not worry about that for now. Okay, let's not worry about that for now. So I pick a uniform random tuple. Okay, can someone, given this description here, okay, so sorry, let me try to put it all in one place. It's a bit hard. Okay, so remember, can someone tell me in terms of the algorithm how am I going to do this? How am I going to do this?
I'm not sure I understand the question.
How do I estimate? Okay, so how do I estimate the expectation of y up to 1 plus minus epsilon for this geometric random variable?
Just doing repeated trials of y until you have. Oh, yeah. By doing repeated trials of y until you have 1 over epsilon squared successes.
Okay, so it's actually technically not repeated trials of y, but trials of the coin flip. Yeah, exactly. Good. So which means that I keep picking clauses until x satisfies 1 over epsilon square clauses. Right? That's exactly. I keep picking clauses until x satisfies 1 over epsilon square clauses. I look at how many clauses I had to pick. And I look at the number of successes, which was 1 over epsilon square, and then I get my estimate. Okay, so now let's look at this a little carefully. Let's first understand what is the expected running time for a single iteration of step 2. That's a single iteration of step 2. Just this. What is the expected running time? So what's this going to be? It's going to be the sum over all tuples. 1 divided by the probability of picking a tuple. The expected running time for a single iteration is going to be this. Now, given x, conditioned on choosing x, how long is this going to take? How long is this going to take?
Less time if c of x is higher.
That's right, but can you express the running time in terms of c of x? So I'll say this is the expected number of, we know what a coin flip is, to get, 1 over epsilon square heads conditioned on there's conditioned on x being chosen. Right? How many coin flips do you need? So you fix x. How many coin flips do you need to see 1 over epsilon square heads? Remember, a success was you were able to pick a clause that x satisfied. How many times do you need to choose clauses to do that?
Just c of x over epsilon squared.
C of x over epsilon squared. No. So the probability of a success is c of x divided by m. That's the success in a single coin flip, single trial. So how many trials do you need? Because you have to do this estimation, which requires you to generate a bunch of trials, right? You need to keep repeating until you get a success. And this is going to cost you runtime. So the probability of a single success the probability of a single success is C of x over m. The expected number of trials for a single success,
Is it just like m over c of x?
exactly, it's yes, it's m over c of x, because that's the expected number of trials for a single success. And then it's 1 over epsilon squared extra. So this is 1 over b times over all tuples of m divided by c of x epsilon squared. Right? And just pulling this out, this is m divided by epsilon squared times 1 over b summation over all xi of 1 divided by c of x. But remember, we just argued that the expected value of 1 divided by c of x is exactly a divided by b, which is mu. So this is saying that this is m divided by epsilon squared times mu. So the larger that mu is, the more time it takes. The smaller your mu, the faster it is. Which makes sense. If mu is small, A is much smaller than B, so all the sets are intersecting heavily. When they intersect heavily, your typical C of x is very large, so you will succeed very quickly. So the expected running time for a single iteration is this much. Okay? The expected running time for a single iteration is that. But the question is, how many trials are we going to get? Now, okay, now let's go back to, we need this so that we can apply the Chernoff bound to x. Right? We need to at least get some number of successes over here to get any sort of Chernoff bound concentration. So does this make sense? This is the expected running time for a single iteration of this step. And then we need to figure out essentially how many steps are going to happen. Again, I'm doing the analysis somewhat loosely just to give you the idea. The formal proof requires a little bit more detail. Okay? Okay, so let's go back to this now. Let's look at the expectation of x. So what is the expectation of x? Let me, yeah, so, okay, so let's step back. The expectation of y divided by m, right? This is what you're adding, is a divided by b, which is mu. So after t trials, the expectation of x is mu times t. So how many trials until x, how many expected trials until x has value c over epsilon squared? This is again looking like a geometric random variable, right? Because the x, it's not purely geometric. It's like a mixture of geometric random variables, but every time you're going to add something to x. The expected quantity you add is mu. So how many times do you need to run this loop until you see until x is going to be c over epsilon squared? What is the expected number of trials?
Is it the same thing, or it's just like the reciprocal
It's the reciprocal
of mu t
of
v over epsilon squared?
so okay, so so one way to think of it, each trial is adding an expected mu to the sum, right? And you eventually want this thing to be something like c over epsilon square. So roughly speaking, t is going to be something like
C over mu epsilon.
exactly c over mu epsilon square. So observe this. If mu is small, t is large. On the other hand, the expected running time of a single iteration, time of a single iteration, is is m mu over epsilon square. Now you see that the mu will cancel out when you multiply them. So the number of trials times the time per trial is essentially m. So I get an epsilon to the fourth over here, and I should say that my analysis is not completely formal. There's a log factor that I'm missing, and I'll get to that shortly. But does this make sense? This is quick and dirty. Like there are more details to be filled out, but this is the idea. The idea is that if the number of trials is going to be small, then it turns out that or rather, if the number of trials is going to be large, then each trial actually becomes cheap. And if each trial actually if trials take a lot of time, then you will actually need to perform fewer trials. So this is what Karp-Luby-Madras called it, was that they said it's sort of it's a self-adjusting algorithm. It's like automatically adjusting to whatever mu is by taking care of these. So this is deceptively simple, but it's very deep. Right? So it says here's your trial. Now unfortunately, the running time of each trial is itself a random variable. So you try to carefully choose it so that you don't spend too much time. So you keep flipping, you keep doing this until your sum is c over epsilon squared. Again, I will say that the analysis that I'm doing is not optimal in epsilon, and moreover, if I do it formally, I have to pay an extra log factor to get some probabilities to work out. But does this sort of scheme make sense? Sort of. Any questions?
Seems like if you do a lot of trials, the chance that one of them is outside of the epsilon confidence range is going to be high.
Good point. Good point. You're right. So if you actually, which is exactly why you need a log factor for convergence. So what I need to do here is to estimate this up to that with confidence at least 1 minus 1 over m. Or let's even do it more, 1 minus 1 over m squared. And then I know that all my trials will be correct with high probability. Does that make sense? I can basically union bound the error. Now how much do I pay for this? I pay log of the confidence. So I pay log m squared, but that's just basically I just pay an extra theta log m factor, right? So if I give myself m log m, then I can make everything work. Now it requires a little bit more thought, but it turns out that instead of estimating this, suppose you simply generate a single, you don't do the estimation. Just generate a single trial and do that. You could also do that. The analysis becomes more hairy, but it's still doable. So you can actually save on the epsilon dependence as well. Instead of estimating up to 1 plus minus epsilon, you just output a single geometric random variable. But I don't want to get into that. I want you to understand this because this in some sense is conceptually easier. You generate this random variable, you estimate it accurately, and then you go ahead and do this process. Now you need to estimate with very high confidence because you're doing lots of trials. But you can union bound over this error. You can.
And to be clear, is that what you meant when you said that estimating the expectation wasn't the most efficient way to do this?
I'm sorry, say that again.
You made like a comment while going through this earlier that estimating expectation of y wasn't the most efficient way to do this.
Yeah, because you lose a 1 over epsilon square factor because of that. So the log m, I think, is sort of I need to check. I mean, I think suppose you just generated a single geometric random variable. Your problem is you cannot apply the Chernoff bound on x because y is going to be unbounded. So then you have to start doing certain things to deal with that. So any questions? Any questions about this? Do you want me to do a formal proof of everything? Like, I mean, it would be a deviation from what I planned, but I don't mind. Like, if you think there's value, like sitting through and just writing out a formal proof and working out all the details.
Of this algorithm, you mean?
Yeah, of this analysis. So right now there are all these things regarding the confidence which I haven't completely explained properly. You have to do a union bound over all of this error, and you have to sort of connect the dots. But hopefully you see the main idea.
If there's a write-up of it somewhere, I'd like to read it, but I think I'd personally prefer if you continue on
Okay.
with whatever you had originally planned.
Okay, all right. Funnily enough, there is no right. So actually, let me end the recording over here, and I'll take questions after this is done.